Hi, everyone. Well, yes, my name is Carla, and I would like to invite you all to go to play.uist.org, where you can find an interactive schedule based on the video previews of the conference. So not only you can plan your schedule by watching the video previews, but you can make your own playlists and share them with everybody. You can make a playlist about your favorite talks. You can make a playlist about your schedule and share it with your colleagues. Or even after the conference, you can share your highlights. So go to play.uist.org and have fun. And we can see each other at the demo reception tonight. Thank you.
Thanks, Carla. All right, so our first talk today is designing a non-contact wearable tactile display using airflows. And presenting this talk will be Jaeyeon Lee from KAIST.
Good afternoon. My name is Jaeyeon Lee, and I'm a PhD student from the HCI lab at KAIST. Professor Geehyuk Lee and I explore the concept and the design of a non-contact wearable tactile display using airflows. Traditional wearable tactile displays transfer tactile stimulations via physical contact with the skin. Various tactile stimulations such as vibration, skin stretch, temperature change, and electric current require a firm contact between the stimulator and the skin. Especially to present a spatial-temporal pattern, every tactile in the tactile display should be contact to the skin. Wearable accessories like bracelets or watches are not usually worn tightly, as firm contact can be a source of discomfort. Therefore, we need a contactless, distance-tolerant wearable tactile display. There are various kinds of non-contact tactile stimulation methods. There are two main categories, energy field-based and airflow-based methods. We chose the airflow-based method because it allowed for a smaller form factor, had fewer safety concerns, and provided a natural sensation. To design a non-contact tactile display, we needed to know several design parameters, such as intensity and duration of a stimulus, and in the case of two-dimensional tactile display, the distance between tactiles. The sensation of an airflow is different from that of vibration. When the airflow touches hair on the skin, the movement is detected by hair follicle receptors, and the airflow applies a mechanical force on the skin. This is detected by low-threshold mechanoreceptors in the skin. Additionally, flowing along the skin surface, an airflow drives the heated layer near the skin and causes the sensation of coolness. Receptors which have different conducting characteristics contribute to the sensation of wind. Thus, the findings from vibrotactile or thermal display could not apply to the design of an airflow tactile display. We conducted 3 psychophysical experiments, and we built an airflow tactile display based on the results, and we evaluated the airflow tactile display in terms of information transfer, and we collected the user feedback on airflow-based tactile experience. To conduct the psychophysical experiments, we built an airflow display prototype. An air pump was used to control the airflow rate, and we used 1 mm diameter nozzles that were mounted at a distance of 10 mm from the user's skin. Instead of limiting ourselves to the usual placement of wearable tactile displays, we consider all locations that could be covered by clothing. We did a threshold measurement of airflow on 29 body locations, and based on the results, we chose 12 body locations for subsequent experiments. Participants were seated in front of the desk, and we implemented the nozzles using a clamp. Experiment 1 was conducted to determine appropriate airflow intensity for each body location. We measured absolute thresholds on on 12 body locations, the duration of a stimulus was fixed to 1 second. We used 2 down, 1 up staircase method and 3 alternative first choice for threshold estimation. These are different experiment settings for different body locations. Sensitivity was different in each of the body parts. Face, neck, wrist, and foot were more sensitive than the torso or ankles. Also, in all body parts, dorsal side was more sensitive than the ventral side. Based on the sensitivity results, we proceeded the next experiment with 6 body locations. Experiment 2 was conducted to determine appropriate airflow duration. We measured airflow thresholds for airflow duration on 6 body locations. We fixed the intensity of airflow to the value that just covered every participant's thresholds because it is clear that the stronger airflow is more detectable. The duration threshold was different for each body location. At all locations, airflow could be detected within 400 milliseconds. Based on this experiment, we selected the duration of the stimulus. Based on the previous 2 experiments, we were able to determine the intensity and duration of a single airflow stimulation. To transfer the spatio-temporal patterns, we need a 2-dimensional tactile display, and we need to know an optimal distance between 2 nozzles. To find the optimal distance between two airflows, we measure distance threshold on the same 6 locations as in the previous experiment. We conducted a 2-point orientation discrimination test with preset distances. To maintain 4 different distances through experiments, we designed a 4-point nozzle mount. The distance between 2 nozzles changes proportionally to the rotating angle. In the 2-point orientation discrimination test, we asked the participants to verify the orientation of the 2 airflow formed. This graph shows the correct rate according to the 4 distances. At the shortest distance, the correct rate is near the 50% chance level. However, as the distance goes farther, several locations showed better performance. We observed that the dorsal side of neck and wrist showed a good performance. So, based on the results of experiment 1 through 3, we built a non-contact tactile display using airflow, and we evaluated the airflow display in quantitative and qualitative aspects. We evaluated the airflow tactile display in terms of information transfer. As a baseline data, we built a vibrotactile display and did the same experiment. We made a vibrotactile display using ERM motors and self-adhesive bands. So these are the parameters for vibrotactile and airflow displays. We made 4 directional patterns. And we asked the participant to verify the direction of the randomly played patterns. Based on the answers, we calculate accuracy and information transfer. The non-contact tactile display showed a comparable performance with that of the vibrotactile display, both in accuracy and information transfer. However, the location of the tactile display had a significant effect both on accuracy and information transfer. Neck is more sensitive than wrist, and it had better performance. Also, we explore the qualitative aspect of airflow tactile display. Participants had interesting comments regarding on the tactile experience using airflow tactile display. For example, a participant described the sensation of airflow as a fine brush in compared to the vibrotactile display as a dull brush. In conclusion, we explore the concept of a non-contact wearable tactile display, and we designed an airflow display based on the results of 3 psychophysical experiments. Our evaluation showed that the non-contact tactile display could be used for transferring information, and the performance was comparable with that of the vibrotactile display. The characteristics of this is the limitation. The characteristics of an airflow are affected by various factors, including the nozzle geometry and applied pressure, and so on. A further study with other types of airflows is needed. We conducted the experiments in room temperature. The sensation of an airflow might be different at different temperature. The results in this study is a lab experiment. A further study for feasibility in a natural environment is needed. The absolute thresholds were basic design parameters for designing simple patterns in experiment 4. To increase the expressibility of an airflow, a further study for JND or SOA is needed. Though we evaluated the human perception and the performance of an airflow display, the prototype is to support the psychophysical experiments rather than a wearable prototype. By using a small fans, we made wearable prototype and attached it by using glasses, collars, and sleeves. And we found the cheek and neck would be a promising location because it showed good performance and the distance between display and the skin remained constant. So I'm ready to answer the question. Thank you.
We have 2 student volunteers right in front if you guys have any questions. While we're waiting, I'll ask a question, I guess. You mentioned a little bit at the end that you made a wearable design. I'm curious, as you shrink down the fan and as you miniaturize the device, how do you have any insights to share about how much does that affect the actual noticeability and strength of the stimulus?
Actually, there is no actuator for wearable airflow tactile display, but we searched a lot of airflow actuators in the market, and we found that those fans are best for one best for our application. However, I think some people can be inspired by talk, and please make an airflow tactile an airflow actuator for wearable tactile display.
Any other questions? Okay, I'll ask one more. Well, I was also wondering if most of your experiments were with people seated at a desk without anybody moving. Given that this is airflow and you feel airflow on your skin, do you have insights on how does the movement, like natural movement, walking, or even just moving your hand, how does that affect the perception of the stimuli?
That is the exact subject I am working on now currently. And I'm working on the effect of the environment, such as the temperature or pre-existing wind, or the effect of focus and the effect of physical movement. I'm still exploring effect of the kind of wearable computing context.
Okay. All right. There's a question right there.
Hi. I was wondering if you could observe an effect of gender or age, so maybe men have more hairs on the arms or
yes.
other body parts, and maybe older people always have a little bit worse perception on the skin.
Yes, the effect of age or gender could be an interesting topic for the airflow stimulation. Yes, we did this experiment with undergraduate students. So this is always. I think this is only for the in their 20s, not for the elders. I'm sorry, but yes, maybe in future we can explore more about to find the effect of age or gender, or yes.
Hi, very cool. I was wondering if you can hear any of those, if you can hear the fans or the nozzles. Is there an acoustic element as well?
I'm sorry?
Can you hear them when they actuate, especially if it's near your face, either the nozzles or the fans?
Yes. In the experiment, we masked the noise from the air pump because it was really huge. So we used 3M earplug and active noise cancelling headphone, which plays the pink noise, and and for this application, we just needed the 3M earplug to mask the effect of sound.
All right. If there are no further questions, let's thank our speaker one more time.